Hello, everyone, and welcome to MacDermid Enthone's discussion on the basics of anodizing, part 2. My name is Robert Collin. I'm the America's Technical Manager and will be the moderator for this event today. The presenter is Sasha Wegner. He is our Anodizing Product Line Manager for MacDermid Enthone. Please submit the questions as you have them in the question box, and we will get back to you via email once the session ends. And again, thank you all for taking the time today to learn about the second part of the basics of anodizing. Sasha, with that, the session is all yours.
Good morning, everyone, and thank you very much, Rob, for the introduction. So today we have the follow-up course from our first part of the basic of anodizing training course. Just a very quick introduction for the people who missed the course and don't know me yet. My name, you've seen that, Sasha Wegner. I'm the product line manager for Anodize in the Americas. And I have relocated over to the US a couple of years ago, taking charge and responsibility for this anodizing product line. But I have been in the industry for almost 30 years now. So without further ado, I want to dive straight in. As I said, we're talking a little bit about the basics of anodizing. And today we'll cover the anodizing bath itself. We'll have a look a little bit into the dyes, organic dyes, and the electrocoloring dyes. We'll obviously talk about the sealing processes, what processes we can use for certain finishes, and then we'll finish up with some of the quality measures we use to guarantee that we actually done a good job anodizing and sealing our aluminum components. So this was the schematic we used last time. The first part, we covered the cleaning, we covered the different types of etching solutions. We talked about the electropolishing and chemical polishing solutions and the differences and different types they are. And last time we finished with the de-smut and with the deox. So as I said, today we're left with the anodizing, the coloring, and the sealing. This is the process flow. Very, very logical process flow here. Again, we're going to start right in the center here with the anodizing tank, followed by the rinses, different coloring solutions we can then utilize for the final optical finish we want. We're going through the sealing process, and then obviously followed by the last few final rinses before we dry the components. What is anodizing? Very, very simple question, but maybe we spend a little time on this. Aluminum itself protects or self-protects by forming a very, very thin oxide layer on the surface. And this oxide layer can withstand very small amounts of corrosion. What we do with the anodizing process is we're utilizing exactly the same process or method here. But what we can do through anodizing is we can create a much, much thicker oxide layer. And this thicker oxide layer in turn will have a much, much higher corrosion resistance. It will have a higher hardness as the aluminum substrate itself, and through that gives also abrasion resistance. And that's really what anodizing is all about. If we look on the right here, this is a schematic of an anodizing tank. We have the extra aluminum part as the anode, where we generate oxygen for the oxidization. Then we have the cathode sheets, which could be lead or aluminum itself. And all this happens with the current from a rectifier in a predominantly sulfuric acid solution. When we look at an anodized surface and we want to do a cross section, it's not easy to do these cross sections, because by polishing the sides of the anodized layer will actually polish over these little pores and channels that run all the way from the top to the substrate. So what we do is we crack the surface, and then we have a look at the side elevation of this surface, and that's what we see here on the left. So the picture on the very left is the side elevation, and what we see here is these channels, the pores you see from the surface. They run all the way down these anodized layers to the substrate, and these channels are really what gives the electric conductivity for any further anodizing and building a even thicker anodized layer. If we look at the anodized surface from the top, so like the bird's eye view, that's the picture here on the right, and we see all these little black dots here. Every of these black dots is an anodized pore, and these pores are extremely small. They range from 5 to 15, maybe 20 nanometers. So extremely small, but there's a vast amount of these little pores on an anodized surface. So when we anodize a component, there are really two competing actions here. We have on the one hand a film forming reaction, and this is obviously done by the electrical current we pass through the component, and obviously the amount of time we leave these components in the anodizing tank. At the same time, we also dissolve the freshly formed anodized layer, and the parameters or the factors that drive this dissolution reaction is the sulfuric acid concentration and also the temperature. So if we choose higher sulfuric acid concentration to get a better conductivity, at the same time we will also increase the dissolution or the redissolution of the anodized layer. And the same goes for the temperature. And this is why temperature is a very critical parameter and factor when we anodize. Any higher temperature will start redissolving the anodized layer at a very high rate, and that's why it is extremely important to control that one factor, one parameter here in our anodizing tank. The electrical current and the voltage will create a lot of heat in an anodizing tank. So and this heat needs to be moved away from the anodized part, and that's really what we do by agitating and vigorously agitating our anodizing tank. This is a schematic of how an anodizing layer forms. There's always a lot of questions about how this anodized layer is actually formed, or is it an integral part of the aluminum component itself, and it really is. So this is not like the traditional electroplating where we plate and deposit another metal layer on top of the substrate. The aluminum and the anodized layer is actually that grows out of the aluminum substrate itself. We see that here quite nicely. After a few minutes, we'll see this aluminum oxide layer growing into the into the component, and because of the volume increase, it will also grow outside of the component, and it will actually increase in dimension. And what we normally say, up to a certain plating time, we'll see an increase of the component dimension of about a third. So 2/3 of the anodized oxide layer will actually go into the component, and about 1/3 will grow outwards of the component, and therefore increase the dimension of components. So here again, this is another cross-section of an anodized surface, and we see quite nicely at the top of the picture the aluminum oxide layer. We see all those little channels, these little capillaries that run all the way down to the barrier layer, and this is really where the interface, where the aluminum oxide layer grows. And then just right underneath this barrier layer, we have the aluminum substrate. A lot of people talk about sulfuric acid anodizing, type 2 anodizing, type 3 anodizing, so on and so forth. I'll just explain very quickly the differences here. Under the mill specification, the type 2 anodizing, it's a sulfuric acid based solution. We operate around about the 20 degrees C, 19 degrees C, for around about 20 to 40 minutes. And we usually say we get about a micron of deposit every 2 to 3 minutes. So that would give us here in this case about 10 to 15 microns. The sulfuric acid concentration normally around about the 165 to 185 grams per liter. Aluminum metal, again, very critical. We have to start with some aluminum, normally around about 4 grams per liter, and then once we anodize and we dissolve some of the aluminum oxide layer back into the solution, this aluminum concentration will increase. And around about 12 grams per liter, up to 15 grams per liter, we'll see a limit, at which point we have to either dilute our solution or use certain ion exchange technologies to remove aluminum from the aluminum anodizing bath. The current densities here around about 1.5 amps per square decimeter. That's pretty standard. If we go much higher than that, we'll see a burn on the components, which looks like a white dusty deposit, which can be seen after anodizing or after sealing on the components. Voltage 12 to 20 volts, pretty standard. Depends a little bit on the jig material we use. Generally speaking, aluminum racks, aluminum jigs have a slightly lower voltage because of the better conductivity compared to titanium racks. Agitation, as we mentioned, we have to move the temperature away from the components to reduce the redissolution of the aluminum oxide layer. So any sort of agitation needs to be vigorous so that we can move that heat away from the parts efficiently. We use some proprietary additives for the anodizing bath, and these additives are really designed to stop the redissolution. They act a little bit like inhibitors on the surface. They protect the anodized surface, and it will reduce the dissolution rate. And a lot of people will actually see that as an increased efficiency or an increased thickness after the same plating time. So that's where this all comes from. When people talk about these additives that will increase efficiency, it will plate faster. It doesn't actually plate faster, but what it does, it dissolves less aluminum oxide from the surface, and therefore it appears that we have a higher thickness and a higher plating rate. So the type 3 anodizing, some people call it hard coat, hard-anodizing. The bath is similar. It's a little higher in concentration sometimes to give a bit more conductivity. But what we do here is we reduce the temperature. We bring that down to around about 0 degrees Celsius or 32 degrees Fahrenheit, and that will really give us the chance, or the anodizing tank, the chance to build much higher thicknesses. So where with the type 2 we reach an equilibrium where we anodize and redissolve the anodizing layer at the same rate at a temperature of around about 0 degrees, we'll be able to plate a much higher thickness, and that's what we utilize for these hard coatings. What we also achieve here is we have a much denser pore structure, and there's a lot more strength within these pores because we don't actually dissolve aluminum out of these pores and reduce the wall thickness of these pores. Therefore, these coatings are much harder and have much better wear resistance for applications like valves, any sort of moving parts. The current densities here are higher, so we operate at anywhere between 2 and 5 amps per square decimeter, and again that helps us to build a much thicker layer in a faster time. The voltage, if we use higher amperatures, is going to be higher again. Agitation, absolutely essential. And what we use here is we can use a proprietary organic additive as for the type 2. For some customers decide to use oxalic acid here. The problem with oxalic acid we see is that it will discolor, or it will color the final finish. If we use it on the type 2, we would probably see a slight yellowing of the surface, which then as a final finish is not very attractive. With a hard anodizing, we'll have a much thicker layer. The layer tends to be gray to dark gray anyway, so this discoloration, this yellowing of the surface is not quite as important as with the type 2 anodizing. So this is a chart everyone can use and then have a look at these effects and factors that drive the pore sizes and the hardness, so on and so forth. And most of this we talked about. So by increasing the sulfuric acid concentration, we get bigger pores, but because of the wall structure and the thinner walls, the hardness will actually reduce. The coloring, because of the higher pore size, becomes better with certain dyes. We have a higher absorption of colors or dye particles in these pores. We will walk down here. Solution temperature. Again, we see the same effect. Higher dissolution rate, so we have bigger pores, or the hardness goes down, so on and so forth. So some of the additives we were talking about earlier. The product we mainly sell for anodizing, especially type 2 anodizing and some type 3 anodizing applications, is the Oxide A42. That's a liquid additive that really prevents the burning. It reduces the dissolution of the aluminum oxide layer, and therefore gives us higher thicknesses in shorter plating times or anodizing times. And therefore it increases the efficiency of an anodizing line significantly. It also would allow people to operate at slightly higher temperatures to get the same surface properties as working without some of these additives. So if someone has problems with their cooling equipment, again, this would be a good way of mitigating those issues and problems. And in general, it reduces operational costs from a standpoint that, you know, if we dissolve less aluminum back into the solution, we have to discard less solutions. We have much longer intervals before we have to reduce the aluminum concentration of the anodizing bath. The Oxidite A44 here, again, most of the additives we sell for anodizing are liquids for easy handling and additions to the tank. This is a spray suppressant, and it's not a wetting agent as most people are probably used to. This is a completely PFAS and PFAS-free product, so that really complies with all the legislation out there at the moment. But because it forms this very nice thin layer of foam on the surface, and it reduces the spray, it helps significantly with reducing attack on any sort of plant and equipment. So let's move on to the coloring of the anodic film. There are really two ways of doing this. One is using the traditional dyes as an immersion dye. These can be organic or inorganic, and these dye particles are absorbed in the pores of the anodizing layer through just immersion. And the intensity and the depth of the color really depends on the thickness we apply to the aluminum part, obviously the concentration of the dye itself, the temperature, and in general the activity of the anodizing dye. Another way of achieving a colored surface is by using an electrolytic color, and these are mainly based on metals such as tin. So I think that's probably the biggest sector here, and there are others that utilizes nickel and cobalt and some other metals to get different shades of color. So this is done in a tank with AC power. So it's an alternating power current source. And what it does is it deposits a small amount of tin onto the bottom of these anodized pores, and then when the polarization changes, it actually oxidizes the tin layer. And depending on how long we do this for and how many cycles we go through, the color we can achieve here is anything from a very light champagne to a dark bronze tone to the final color, which would be a very, very deep black color. So because this deposit really appears and is generated at the bottom of these pores, these colors have extreme good light fastness. They're very well locked in and therefore give extremely good performance. And we see that here a little bit better. On the left, this is just our immersion process for organic or inorganic dyes. because of the size of the dye particles and the size, the very, very small size of the anodized pores, most of the dyes get absorbed in the top part of the pore, and they're really locked in this top part as well. So you can imagine when these parts are subject to any sort of abrasion, this layer will slowly wear away, and we lose some of the color depth as well. Also, they're a lot closer to UV radiation, therefore the light fastness is a little bit limited when it comes to these organic dyes. On the other side, if you look at the electrolytic colors here, they're deposited right at the bottom of these pores. The whole top part of the pore will get sealed and will close up, and it would take a long time for abrasion to actually get to this bottom part of the pore to influence the color depth or the color shade of these colors. So therefore, electrolytic colors, more cost intensive, obviously, to apply them, but for outdoor applications, really the best choice. So we see that here again, organic colors here in the top third of the pores. Then we have combinations where we have a electrolytic color combined with an organic colors to get even deeper shades of black mainly. And then here right on the right hand side, we just have that tin coloring solution that deposits the tin and the color at the bottom of the pore. So when we look at a cross section here, and I hope everyone can see that, and maybe we'll go from the bottom here. We see the aluminum substrate here with a clear dividing line. Then we have a porous anodic coating, and then we see the part where we don't really see these cavities or these channels anymore. This is really the sealed surface where the pores swell and they close up. And then right at the top, we actually see the organic dyes. So these are obviously the immersion dyes, and they're really only in the top part of this anodized layer. Oxidite dyes, we have introduced a new range of dyes, organic dyes, for the Americas market, and these are for indoor applications, therefore exterior applications. They really have very high light fastness, UV resistant. So there's an application, there's a dye for every application here, which we can offer and provide if there was any need. What we have done is there's a lot of sort of custom colors out there. We have done some work with our dyes to match these custom colors. And again, if there are requests for doing something like this, please contact us and we'll get in touch with you and work you through the process. The sealing, the final step of the anodizing process, really, and probably one of the most important process to get all the good properties we expect from our anodized layers, whether this is corrosion resistance, UV resistance, abrasion resistance, and so on and so forth. And when we look at the sealing types, there are really three types we use. The old traditional hot water seal, the medium temperature or nickel acetate seal, as some people refer to, and then we have the nickel fluoride seal, or a lot of people refer to this as a cold seal. And when we look really at the temperatures here, I think we very quickly figure out why people like to use the nickel fluorides, the cold seal, around about 30 degrees. There are huge cost savings as opposed to using a hot water seal that works at around about boiling temperatures. Some people actually use steam even at higher temperature to have better sealing properties and slower sealing times. And again, if we look at the sealing times here as well, we have huge advantages with the nickel fluoride cold seal here, sealing around about 15 minutes for these parts. One of the downsides for the cold seal is really that it interferes with some of the organic dyes. So generally speaking, when we talk organic dyes, a lot of people will still use the nickel acetate seals. They're more stable. They don't attack the dyes. It will not change the color shade significantly, and therefore really the process of choice when it comes to organic dyes. If we look at the seal surface here, and this is the hot water sealing mechanism. What happens here is we created an aluminum oxide layer that does not have any crystal water. So through the immersion in hot water, hot deionized water, we will actually reintroduce crystal water to the oxide layer structure. And this reintroduction of the crystal water will actually swell the oxide layer. It increases in volume, and the way it can only go is inside the pores, and in that way it closes up the pores. This is slightly different to the nickel sealing mechanism. And what we see here is this works more like putting a cork in a bottle. So we precipitate nickel inside these pores, and through that precipitation we will plug the pores, we will close the pores, and really sort of cut it off from any outside attack of the environment. This is for the nickel fluoride, the cold seal. The nickel acetate is a little bit of a combination of both these sealing mechanisms. It precipitates nickel into the pores, but at the same time, around about 80 degrees, we'll have a rehydration of the oxide layer as well, and that will further help closing up these pores, making that structure more compact and give very good corrosion resistance. So the products we offer here for the hot water seals, these additives are really designed to prevent sealing smut. Whoever has anodized in one of their previous lives knows that one of the biggest problems every anodizing shop has is dealing with sealing smut. So it's a white powdery deposit on the parts after sealing, after drying, which needs to be wiped down, cleaned off. Sometimes it can become quite tenacious. So for the hot water seal, we have an additive here that goes into the final rinse at very, very small concentrations. The Oxidite S69 and S59. These are nickel fluoride cold sealing products, again as a liquid or as a powder product. And then the nickel acetate or medium temperature products here, we have two. The PS2 is really developed as a pre-seal, which is then followed by a nickel fluoride seal for the final sealing. And there's a new product that has just come out, which is the XD7918, which is a new acetate sealant as a one-stage sealing process. It contains a wetting agent for dewatering the surface, which helps again with the drying of the components, and it prevents sealing smut significantly. And one of the big benefits, it has an extreme long life, which is good for any sort of effluent treatment and cost associated with that. So anodizing quality control, I'm going to spend a little bit of time just running through some of the things we have to do to really make sure that we meet the specifications and meet all the requirements. I think everyone knows the Eddy-current meters here. It's a non-destructive way of measuring thicknesses, and thickness is really one of the most critical parameters when we anodize. It really determines the corrosion resistance. It determines how much dye we can absorb in the surface, and what it also does is it determines how long we have to seal the surface for. If we don't control our anodizing thicknesses, if we choose the wrong time in the anodizing tank, sorry, in the sealing tank, we will not achieve certain criteria to meet the specifications. So this is the dye spot test, and a lot of companies use this test to determine the sealing quality of the anodized part. So what happened here is we use a acidic solution, normally sulfuric acid and fluorosalicylic acid. We drip that onto the surface of the sealed and finished component, and we let it react on the surface. And depending on the quality of the sealed surface, it will open up these pores more or less. For a good quality sealed component, it will open up the surface less. For a poorly sealed surface, it will actually open up these pores significantly more. And what we do then is we rinse off this acidic solution and we apply a drop of dye onto the surface. So for surfaces that have been opened up by this acid, they will absorb a significant amount of dye, which will then be reflected in a color change of the surface. So what we see here in this table is from the top where parts have absorbed a lot of dye, and this would be a very, very poorly sealed surface, and it would be a no pass. If we work down this table here, we'll see the bottom two pictures where you can hardly see any change or coloration of the anodized surface, and this is really what we're aiming for, and what would determine that we have done a good job sealing the components. There's another test, a different test for determining the quality of the sealed surface, and this is the mass loss test. It works in a similar way. We're actually submersing a known surface area in an acidic solution. which is normally a phosphoric acid based solution, and we let it react for a certain time. We take weight measurements of the components before the treatment and after this treatment, and we'll calculate the difference in weight or the weight loss for that particular surface area. And from there we can really calculate per square decimeter how much weight, how much sealed surface we have actually lost. So for Qualinode, for the European specifications, they really request less than 30 milligrams per square decimeter. For the AMA, the North American specification requirements, they specify 40 milligrams per square decimeter here. And that's really brings me to the end of my presentation for today.